trying to do right now is to insert what do you call them? Baffles.
Yes.
Here in the middle, that will play the same role as the annulus I was talking to you about, in order to sort of pin down the shear in the middle. That's what they're after. The picture I was describing doesn't put so much confidence that this will be able to self-generate. But then again, it's a different geometry and it should be tried. And the advantage of the Wisconsin setup is that they have all these measurements around the sphere that makes them able to reconstruct what is the magnetic field inside. And this is very good, and it's something we don't have.
But
So
the baffles are not soft iron, or are they soft iron then?
I think the one they've machined now is stainless steel.
Right, so it would be
Do they have probe inside too?
Yes, they have probe inside too as well. So that's what they're doing. The group around Dan Lathrop is now only concerned about operating the 3-meter system. So the 3-meter system is one sphere, 3 meters in diameter, with an inner sphere which is 1 meter in diameter. Okay, and that sphere has been operated up to now with water inside, and with water inside they've checked a number of regimes because they can rotate. So there's a shaft here that rotates the inner sphere, and the whole thing here is the outer sphere can be rotated independently. All right, and what they've looked at is the various hydrodynamic regime you get depending on the rotation of one and the rotation of the other. Okay? And they seem, in that particular case, what they seem, so all these are smooth, all right? So the entrainment is through the boundary condition, the boundary layers, and what they see mainly in these regimes are inertial waves. Okay? So they're moving in regimes where a lot of the transfer of momentum and energy has to go through inertial waves, which is, I think, very interesting
right.
to see what will be. Yeah, it will be very interesting to see what is the magnetic behavior in a system where inertial waves are dominant. Now, similar to this is a much smaller experiment. It's the same scale, but this is only 60 centimeters that they have in Grenoble, right? And they've been operating it. It's the same thing. They can be rotated independently, but in the measurements they've made, this is a very strong magnet. Okay, so inside the inner sphere is a permanent magnet, and what they have studied up to now is what is the hydrodynamics of a flow that is rotated and has a strong magnetic field imposed to it. Now, it's not the dynamo, so you're assuming that the dynamo is just producing this, right? And then again, they've been trying to identify all the waves and rotational waves, and it's a zoo, right? I don't know if you guys have ever looked at the of the zoo of waves. I couldn't come up with the name of Andrew Jackson's students. Does anyone remember? Andrew Jackson had one PhD student who graduated about 3 or 4 years ago that sorted out. No one's helping me. I'll try to find out. That sorted out. Right. All these modes. What you see is when you do measurements in there by measuring the velocity, you see the propagation of all these range of modes. Some of them are fairly easy. The inertial modes are fairly easy to relate to what has been observed in Maryland. And then you have a bunch of other modes that don't really seem to collapse on the predicted dispersion relationships. But that's what they. So that's experimentally what's going on in these geometry.
So, Sie ist slow magnetosonic waves or and Alvin waves, or what are the types of modes, or magnetostropic?
The ones that have been identified for sure are the inertial waves and one type of magnetosonic. Alvin waves seem to be damped fairly. It's a question, one open question, but I don't know if there's an answer for this in Riga. The Karlsruhe people suggested that when the dynamo starts, you have in the spectrum some peaks that could be attributed to Alvin waves. All right? Is there any evidence of that in Riga?
I do not know. I presented this spectrum. I explained where is propeller frequency, where is wind frequency, but I never thought about Alpen frequency. Maybe that it is there.
Because in some parts of these experiments, like in ours, the magnetic field gets to be pretty high. So the Alvin speed is not small anymore. You can get Alvin speeds over meter per second. This is not really small compared to all the other frequencies.
And then, of course, the frequency should shift in an expected way as you change the magnetic field, or as the dynamo itself changes.
That's the point of where it will be very interesting to look at the outcome of further studies from these experiments, because they will be coupled with other types of waves that don't make it the simple Alvin waves where nothing is moving. You impose a strong magnetic field, you do a disturbance, and you can look at the waves propagating. Now it's the whole thing is there: rotation, Coriolis force, and the coupling between these waves. And this, for now, I don't know.
Our field is alternating field, and it means that the whole field pattern rotates, and there are waves. Of course, our field is strong enough. We should check maybe, and we can find some.
So, if you want to check for waves, numerically, how is it that people, when you see, when you want to, you pick up a disturbance somewhere and you want to attribute it to a wave, the only thing you can do is a dispersion relationship, right? Or a phase relationship, meaning that you have to measure in several points and look at how the phase varies between these points, or construct a dispersion relationship. Is there any other way?
Maybe not, and even that is not easy, because the frequency will depend on the length, wavelength. And if you have a domain with rather complicated geometries, or different things, I don't know. You do have, of course, a cavity, because you have the container.
But has this been done numerically in some of the simulation you describe, or you evolve the flow and you build a magnetic field and there's some back reaction and people try to isolate if waves are playing a role? Like Alvin, magneto, rotational.
I mean, for unstable modes, of course, and MRI modes can be unstable. And so that's what Dan Lethrow believes to have seen, of course.
Yes.
Because he has this diagram in terms of two different term numbers, or over again. Yeah. In and outer, I think, simply around somewhere. He finds a cone where he finds the modes. M equals 2 and 1 more, so I believe it was 4. 4.
So, I had a question actually. I mean, the discussion was. I mean, if you, I'd be happy to answer questions that you guys have on anything about related to the experiment. But in addition to that, I have a question. So, from what I described, it's possible to make a dynamo with interesting, possibly regimes in the lab. So, what is it? Is there anything that we as MHD hydro people haven't thought of that you guys want to learn from an experiment like that? It's a tool. It's a tool that, in a way, simulates an experiment with a Reynolds number of 10 to the 7, a magnetic Reynolds number of the order of 50, if you want to put it a number, and that generates a magnetic field that has turbulent flow field in some configuration. All right. So, what do you guys expect to learn from it? Is there any what can be done?
Maybe it's not a direct answer, but you have argued with specialparticle. But mean field theory offers a few other possibilities to have, together with differential rotation, a dynamo. We yesterday discussed this omega plus J effect. And there are also such effects. Has somebody thought about such possibilities? And at the same time, to come close to your question, you could look whether such effects, but other effects, different effects, are possible.
Yeah, how would you look?
So
to me.
To you. To you.
To me, right.
Yeah.
So, the first part of your question implies that one is able to reproduce the same thing in a strong rotating reference frame, right? This is what you want to J.
Yeah, you have a rotation close to it. And in this way defined an axis for your omega axis. And you have irregular motion. So such an omega plus J effect, which would drive a current parallel to the plate, or how to say, in asymptotic direction, could be of interest.
Maybe you should draw a picture, or a pictorial explanation of the omega cross J effect.
Yes, please.
So now it's your turn.
You got yourself into trouble,
Yeah, I could try it. Let me start with the alpha effect. It is often said that the alpha effect can be explained in this way. This is an original straight magnetic field line, and if you have a motion here, then it is deformed in this way, and then it is twisted, so that you have a magnetic field. I don't know whether the arrow is not correct, but you have a magnetic field loop, and it is again connected with a current. So this explains why you have electromotive force which drives the current in the direction of. Okay, of course you have at the same time opposite loops, and you would have this current, and these two effects would compensate each other, except you have a gradient of say turbulence intensity, so that the effect here is stronger than the effect here. If you have here a gradient of u squared or so, then the effect is here stronger than here. And only then, consider here another field line, these effects don't compensate each other. You have here a smaller current, and you have, so that you have a remaining component. Okay, omega equals J. I think you have the same, you have not the argument that this effect is, or these two effects are not equal, so they would compensate each other. But if you have here a stronger magnetic field than here, then you have a reason that again, as this current is smaller than this. It means if you have not this, but you have a gradient of the magnetic field, say B over Z, B over dz, you have the same effect. So the same explanation I gave for the alpha effect, with a gradient of the turbulence intensity, applies if you have a gradient of the magnetic field. And that, you remember, I said omega plus J or omega plus curl B can be written in two terms. You can resolve this double cross product so that you have a gradient, which is without of interest in induction equations, and you have omega gradient. This is what I mean with a set derivative. So this is an explanation why you have this omega plus J effect, also in a homogeneous turbulence, and you have not this term, but you have a gradient of the field. Yeah, okay. You said I should try to draw a picture. We have then to think about what happens close to your rotating disc. Have you such? But maybe it could be a starting point for thinking about the situation close to the rotating disc.
Yeah, it sounds indeed much more plausible, perhaps, for laboratory experiments, wouldn't it? Because, I mean, as you are saying, the magnitude of this effect should become significant if J over B, let me call this somehow, as I did before, K1, if that becomes comparable or bigger than the stratification that you have in the domain.
Oh, there is no stratification, right?
Exactly.
Exactly.
And so therefore this is small, and therefore the omega of J effect should always win in many laboratory experiments.
But you can have an alpha effect not.
Yeah. From boundaries, you mean, right?
Yeah.
Or what?
No, not good argument.
Why not? What?
Well,
What were you saying?
I think you don't need the stratification if you have another reason for a gradient of the turbulence intensity. The stratification is in the usual way of reasoning only used to have a gradient in the turbulence intensity.
Yeah, right. So that means like this.
But there's, if there is, so in the setup we have at the moment, the only way to create some sort of a rotation, like global rotation, like you would like to have here, the only way to do that, as I explained now, because we cannot, or we do not rotate the outer vessel at the moment. So the only way we have to do that is rotate those two propellers at different speeds. Okay? In which case there is one additional component of swirl which comes.
Why cannot you rotate them in the same direction with the same speed?
Yes, I could. Yes, it's the other possibility.
That's a real washing machine then.
Yeah. But you don't really use this, is that what you need?
That would have them rotate in the same direction, but then you would have a swirl. If you do that, there's a few changes. change number one is experimental. Every time we try to do that, we have problem with the pressure and cavitation. But then you can say, this is your problem, why don't you go home and solve it?
No, I'm very sympathetic.
So it's problem number one that has prevented large attempts. When we rotate them too fast in the same direction, we have all sorts of hydrodynamics problems. Okay, but you could think about doing it. There's an important change in addition to the global rotation when you do that, is that the helicities that are induced, because you have the pumping in one direction here you reverse the pumping but not the rotation. So the local helicities are reversed. Okay? So no longer do you have a thing where you're adding helicity.
But this is good, for this mechanism it's good.
So yes, because then you would expect you have to see something new. Alright? What I tried to explain yesterday is that when we start the differential rotation here, the dynamical regime we see do not invoke a further mechanism. You don't need, it hasn't been needed to invoke something more that would crucially depend on the rotation to get a new effect. Alright? We could just understand from what we had with equal rotation and saying that they interact, and that would build the phase diagram I described. Now, if there is a new effect that is associated with the J cross B term, then you have to see the building of something different, possibly that strongly depends on rotation. Or what we've seen is that the kind of rotation we induce, but rotating the speed, counter-rotating the speed, the disk at different speed, produces a magnetic behavior that can be explained by the interaction of the two basic nodes that we have. So we haven't put more into it. Mm-hmm. So in that respect, I think we failed so far at exhibiting a new effect of this kind, because it wasn't needed. Now the suggestion of doing this, of course, is a very good one, but now at the moment is hindered by engineering problems, because you really create a very strong vortex. All right, so you think about the mechanism of vortex stretching that you've learned at school. All right, which is even the Berger's vortex, is you create a body of fluid that rotates, and then you stretch it. This is exactly what you do here. You create a body of rotating fluid, all right, and you stretch it as much as you can. Mm-hmm. What happens there is very so as you stretch, the rotation increases and the pressure decreases very strongly in there. Okay, it really decreases.
Don't rotate it that much. Do it gently.
So when we rotate gently,
what is the threshold for this? Okay. What omega you need?
So for rotating gently, about a third of the max speed that we've had in counter-rotating thing, we haven't seen anything spectacular. We don't reach dynamo action. Because presumably it is not rotated fast enough, because when only one disk is rotated, you can have that. But when you're producing that strong stretching, then the cavitation is giving us all sorts of
Comments, what are the critical values of omega? Probably higher than what are the critical values of omega for this omega cross J effect? Probably higher than what you expect for alpha effect or other mechanisms, right? Or not?
You see, if you think of turbulence also, for the alpha effect, the gradient of the turbulence intensity is of interest. For the omega cross J effect, the gradient of the magnetic field. And in Oliver's calculations, the omega cross J effect was important at a place where the gradient of the magnetic field was strong.
So maybe we can get away with slow rotation if you manage to launch this mechanism.
One could also think of just measuring the EMF element by imposing a current. on the rotating system, perpendicular to the direction of rotation. Can one do that? Putting just some electrodes on the sodium?
Make a drawing. An experiment has to start with a drawing.
Yeah, I mean that's something which one wouldn't really be able to do in simulation so easily, but so looking from the top, we would have the cylinder like this, it's rotating, and you is omega, but now you have two electrodes here. So you have a plus and a minus, you send a current through the whole thing, and then you measure the electric field along the cylinder. So now the question is, well, that's your thing here. No, that's not right. No, it would be in this direction then. Here you would need to measure, right? Yes. So here you have your battery. How does the battery look? Like this, and then here you measure something else.
What is the idea behind this?
Omega cross J, electromotive force, omega cross J.
And of course the cylinder would hook probably is turbulent, right?
So wait a minute. What you want out of it is that if the EMF is omega cross J, am I correct? And the J is imposed. All right. And you're saying that so. All right.
There's a minus sign maybe.
There's a minus sign.
Put plus minus, you will be right.
Excuse me.
Put plus minus, you will be right. The directions are important.
But you want that EMF to be the in the measurements. You want that EMF to be the gradient of the potential.
Yeah.
Why? You want to make it a curve, right?
Yes, that's right. You wanted to have a curl.
Yeah.
I mean, what you're going to measure in these things is related to the question. One question we're discussing with Anwar, with Agris is so the thing you operate from is this one, right? This is what current is in this system. Now E is minus grad of a potential minus dA dt, right? Okay. Now, if you want to say that the potential difference you pick up is related to this, which is related to this, okay? Well, the first thing you have to do is do something with this term. Okay? And then the J you have is the one that you've imposed plus whatever other induction processes take place. Because you input currents, the currents get distorted, and the distortion of those currents produce a magnetic field, and that magnetic field produces a current. Little j is just the curl of H.
But then don't measure the potential, right? If it's so different. Can you measure the current density in the correct direction?
I think it is okay. If you produce an electromotive force which makes a potential difference, then you can measure it. And the fact that it is a gradient is, and the gradient plays no role in the induction equation is not important for this measurement.
So what do you do with this term?
What?
Drop it. Yeah. All right. Drop it. say that this is small, forget about that, so get back to J equal to J naught, and say that the gradient here is the omega cross J. Yeah?
Yeah.
That's what we started with.
Yeah.
Okay? So,
No, but this may not be true.
is a large number of assumptions,
It's
all
only
right, that have gone
maybe not the gradient
into
of
doing
anything,
this.
right? Or it can have only a small potential part. You know that its curl is supposed to be significant, right?
Sorry.
We know that the curl of omega cross J
Yeah.
is supposed to be significant. Otherwise, we won't start this discussion at all.
Yeah, but I think the problem we discuss now is does such an electromotive force occur?
Yeah.
But
But imagine that it's not equal to the gradient of 5, or only 5% of it is potential.
I think
The rest is vertical. Then your measurement will fail, because this potential difference will be negligible.
What would be the potential we'd have to apply to that thing in order to have a coherent flux of electrons across all that messy vortex?
No, I can replace. That's the not so bad part. I can replace that potential generator by a current source. Right? I can put here a generator that will give you 10,000 amperes if you need that. All right, okay. I'm just saying I put an electrode right in here, and I put an electrode right in there. And if I'm saying the potential difference here is very small because it's a conducting fluid. All right. So with a potential difference of a few volts, let's say a few 10 volts, you're going to get a few hundreds of amperes right across. And chances are, I agree with Axel, that if you do this in the middle, the currents will choose the easy path. Okay, so you can do. This is perfectly feasible from an experimental point of view. And then you will measure the potential difference across.
You measure current directly, current density, in that direction instead.
I don't know how to measure current density.
By looking at a potential drop, right?
But again, you mentioned that
Yes,
it's not the potential.
It's the one point. You remember what I gave a picture of just the simplest omega effect in a closed box. And I was making precisely that point that Anwar came back to it, is that not all of the currents are driven by a potential. You have a direct U cross B induction term, but you have a potential term, and they don't operate in the same neighborhood. So depending where you measure, you might get a potential response or just an inductive U cross B response.
I think this discussion about the potential is, how to say, it doesn't lead is important. Think of the old Riga alpha effect experiment. Say, put some flow, it was a flow from which we think that it will produce an alpha, in a magnetic field, and then they measure the voltage between these 2 points. Or the potential difference was measured. And it was interpreted as a existence proof of the alpha effect. So I think what we discussed about potential and not potential, it is just for measuring this effect with an instrument outside the fluid. It is okay.
I agree with. I was just debating on how to do it, but I agree that ultimately, if you pick up a signal, you can show that it has wavelengths. But my question is what Axel proposed meaningful for the J cross B or the J cross omega term? That is, I'm injecting current in the experiments, I rotate it like this, and I try to see if I get a potential difference across those 2 points.
It seems reasonable to me. Here, you put a magnetic field in order to measure electromotive force given by alpha times b. And why not give a J in your experimental device and measure whether you have an electromotive force. You have an omega defined by the motion in your device and measure an electromotive force omega plus J. It's not rather analogous.
Okay, if it is that the reason why I'm pursuing this is that this is highly feasible, right? So it's worth discussing it for a moment. So you inject with two electrodes a current that will mainly tend to do this. Okay? Mm-hmm. In doing so, you've generated a magnetic field that is like this. Also, there's no way that you can avoid that. Okay? And what you want to do is to measure a potential difference between this point and the one on the other side.
Yeah, yeah.
Right? Now, if I just have... Now, I will have a rotating fluid. I'm rotating everything in that direction. Okay? I have a rotating fluid that will do something like that. Right? So, just the induction of that, what does it give? I have a V cross B term here, and on the other side, V going like this, cross B going down like this. So just that induces a potential difference. Okay?
Basically, yeah.
If there is no J cross omega effect, I still measure a potential difference between those 2 points, which is due to the induction I get from that magnetic field I produced inside, right?
What
This
is
is
the
a
sign?
sign.
You must have
Yeah, it's interesting.
an omega at this place. Either Coriolis force.
No, omega, you rotate.
Or,
Yeah, I'm doing what Axel suggests.
or the rotation of the fluid. And it's a curl of, the mean velocity.
Yes, yes.
And maybe you have no mean velocity or no quantity which you can interpret as mean velocity just at this place. You have it here and here, but not in the middle. If I...
All right. Because in the middle, you immediately start the difficulty, right?
Yeah, I think
because
there
then
could be a
you will have, if I impose the current and I measure the potential difference, this will be linear in omega. Same thing here. If I impose a current, I produce a field, and as I rotate, the potential difference will increase.
Probably their signs will be different. Probably their signs will be different. The plus sign of the one of them is definitely sensitive to the gradient of B.
So
The other is not.
can we go back to signs and put them, because this one is easy. If I rotate like this and I impose a current that is flowing in this direction.
But then invert the arrow, right? Or the magnetic field.
Did I do that wrong? If I impose a current that
Then
is
it's okay.
in this direction, then the induced magnetic field is indeed like this. Yes? Okay. And if I do that and I have V like here, B like here, that's an EMF that is in that direction here. On the other side I have V like this, B like this. I have an EMF that is also in that direction. Okay? So if I called phi 1 here and phi 2 here, I will have phi 1 minus phi 2 negative. It's hard on the board too.
You speak about an effect which exists
Yes.
in the absence of fluctuating motions.
Yes.
But the omega cross J effect is in fact made by fluctuating motions under the influence of
of the coherence force.
Okay.
So-
So that's
I
how
think this
good.
argument is too simple.
No. It's going to be added to this.
Yeah.
Okay.
I also said there will be a
So-
background signal.
So you're going to have delta phi equal delta phi related to mean motion plus delta phi, phi 2 minus phi 1, related to fluctuations.
Well,
Right?
can you estimate this delta
Now,
phi mean?
let's look at this. Look at the scaling to start with. Delta phi due to the mean will be linear in
Omega.
the angular rotation omega naught.
And J.
This is linear in omega naught, and this is linear in J naught. Okay. Now, how does this one scale?
In the first approximation, in the same way. We speak about an effect which is proportional to omega plus J. But it's an effect which is caused by the fluctuating motions.
But the fluctuations will depend non-linearly on omega. Therefore, when you will be
Yes.
changing,
Is it sure that
I think we should make things simple. For not too large omega, you have a linear effect.
no alpha the one you described here in your drawing? Okay.
Yeah.
Immediately in that drawing, if you call u the intensity of the motion in the Riga, or the one that I described in the VKS, and you plot this as a function of u, it's quadratic.
Yeah.
Okay? So in that case, the result was clearly quadratic. And any linear effect could be attributed to something else.
The coefficient here should be also quadratic in the fluctuating velocity.
So, okay. So and since omega
But
naught, and
not
since
quadratic in omega.
no. But since I'm talking about omega naught, the one that is driving
wait a
the
minute.
flow.
First right proportional to u dash squared.
Proportional to what?
U dash squared. Velocity perturbation squared. And now tell me how your fluctuations, velocity fluctuations in your laboratory depend on omega.
So it will be proportional, if this is proportional to u prime squared.
And on
Then-
top of that, on
let-
omega.
Let me
On top
finish.
of that, on
Let me
omega.
finish. If this is proportional to the square of the fluctuations, this term,
And
that-
on omega. Also on omega naught.
then in that case it will be proportional to omega naught squared.
This is what I'm saying, yes.
Sorry,
Omega naught.
naught is
Omega naught is the one I impose in the lab. Okay,
I
it's
think
my
we
button.
should discuss only about omega naught. So it is also the quantity which influences the fluctuating motions.
Exactly. So if it is, if these effects, if what you call omega cross j from the fluctuations is proportional to the square of the velocity fluctuations,
Don't write it that
then
way.
this will be quadratic.
On the left, write u dash. On the left, in front of omega, write u dash squared, right? Is it correct or not? Correct or not?
Yes, times tau
This is
squared.
okay.
Times the tau squared, yeah?
And this is you can consider it as a velocity of the fluctuations in the absence of rotation, and it is slightly disturbed by.
Yes. Okay.
But then this depends on omega, another omega. You have
Okay.
lots of omega zero.
No,
I think you can say
So my
this doesn't depend on omega, or the omega influences it's there in this linear term.
So if we do this to answer your question experimentally, my prediction is that you will have a linear term, which is due to the mean motion, and then you have an additional quadratic term that possibly is the omega cross j effect. Yes.
It is not quite, at least in the first approximation. It
This
not
is
quite
u
right.
prime is u prime is proportional to
But
omega
Karl-Heinz,
naught.
without omega in his apparatus.
Yes.
Karl-Heinz,
It's
so
in my
without
apparatus.
omega.
Sorry?
Without omega in his apparatus.
There's no
dash is
motion.
equal to 0.
Is if omega naught is equal to 0, there's no motion
You
inside.
have here U, and now the U is slightly changed by something omega.
No,
And here
It's-
also
it's
U plus,
no, Karl-Heinz.
and you can expand it. You
No,
have
no.
first the term which goes with omega,
Yes,
next term with omega
yeah,
squared.
yes, but
But
Ka-
it's
Karl-Heinz,
identical 0. Because
Karl-
U is identical 0.
Karl-Heinz, in the experiment,
Yeah.
if you do not rotate the fluid with omega naught, the
Yeah.
fluid does not move.
Yeah.
There is no U which is associated with no omega.
Linear term vanishes.
Yeah.
The flow is created by omega naught. And so the fluctuations are created by omega naught.
Yeah.
It's unavoidable.
In that sense, you
So that's what I'm saying, that you will have
You may be
this
right.
term here will be quadratic. And this is exactly what happened in all the measurements of the alpha effect that I know of. Which actually are 3 of them. I know
Yeah,
the
I
Leonard
think I must-
experiment, I know what you've done, and I know what we've done in Kazakh.
I must say it.
Okay.
Let's make a bet if it will work.
All right. Same as last time.
So, wait. Are you saying yes or are you saying no?
I'm saying that this works.
Me too. There is no bet.
Oh, but so the enjoyment is in the bed. So I'll
We
say
shall
that-
decide who
I'll say
loses,
that
right?
it
We
doesn't
shall
work.
drink wine, but we shall decide who lost.
Yes, August.
Can I add some words about this soft iron? So, it seems for me at least that soft iron is enhancing alpha effect approximately twice. Why? If we, where I can draw. So, if we have this rotating disk, and if we assume that alpha effect is producing current, this current is current loop close to this disk. If this disk is stainless steel, then nothing more can be said. In case if there is soft iron, then, and if this soft iron could be infinite, then as it is written in many textbooks, then you can calculate magnetic field drawing this mirror current on another side of this, and the result is that with soft iron this almost doubled. A magnetic field produced by alpha effect is almost doubled. Is it so?
I think it's a very valid point.
Yes. Another question is, what is this omega doing there? If there is this magnetic field, and if disk is rotating, there is produced currents in such a way. And for such currents which are producing magnetic field in azimuthal direction, this iron is doing nothing. So it seems for me that alpha is alpha times 2 approximately, but this omega effect is not for the first instance changed. But of course there is another problem, that there are wings, plates on this, all this. These plates also are ferromagnetic, and then there is more complex investigation needed what is doing with alpha effect because these blades are there. That's about this problem. About problem which was raised here. The usual situation is that this omega is rotation, omega G effect. It is rotation of the whole object. And this current is rotating, G is rotating together with the whole object. So, this effect of course exists, but you are seeing that this current is on fixed direction. But if it is, for instance, on sun or something like, where the whole object rotates, current direction is fixed, then of course this problem is simply not rising. And then alpha, this J omega effect is as Karl Heinz explained.
Okay. So
What does Karl Heinz say?
This effect exists, of course, but this is not G omega effect which Karl Heinz have in mind. And to have this, current should stay on spot and object should rotate.
yes, that's what's happening. The current stays here and the object rotates.
Yes, but this is one turbulent eddy which rotates. But when Karl Heinz is writing omega, it means rotation of the whole object. It's so. The whole S,
by the vorticity of the mean motion.
the whole S, or some or sun or some star rotating with this omega. So.
Yeah, but
That's why I said perhaps this effect is not in this middle plane, but it is close to the beats. This is the rotating phase.
Okay.
Yeah, symmetry plane can be dangerous.
All right. So to put it short, if we rotate slowly, that part should not exist. There should be something quadratic. It should be linear. That can be checked. That can be checked. That.
well, Agris is saying it should be quadratic, yeah? That's
Well,
what you're saying?
No, he's saying that doesn't exist. He says that there is no contribution from the rotation of small scales in the system like this because you don't rotate the current with the rest of the object. Therefore, you are not in a reference frame that is rotating as a whole. You still have kept your old reference frame, which is the lab reference frame, which is not moving. And this is not the derivation of the whole thing. That seems to be a valid objection. On this, agrees.
Yeah.
What I have to say is, I think this one is a very valid statement. The fact that you could compute the current by taking the image of the loop from the other side, therefore having an enhanced alpha, I think is a very valid point. As in regards to omega, all I'm saying is we made an omega measurement. Okay, so we measured the strength of the induced omega effect in the experiment with stainless steel and with soft iron, and it was tremendously increased. So there is a change. It was something that was related to the omega effect, and there was a strong increase with the thing. And as I said again, the way I understand it is that if the magnetic field line connect like this, and there's shearing here, you induce the boundary condition is forcing on you an additional shear, which turns out to be an omega induced field.
This boundary condition, of course, is this boundary condition means that you are seeing this mirror image.
Yeah, but that's for
Any mirror image, and that's all. The currents going in this direction are not changing any giving no input into perpendicular magnetic field. These currents are producing azimuthal field. So, of course, if alpha effect is enhanced, you can enhance also result.
No, because
This is only difference there is only difference in words. Difference in words. I said alpha effect enhanced.
No, it's not difference in words. This is the frequency of rotation of the disk, and this is the measured induced field. If it is an alpha effect, it is quadratic in F. It is not linear. It's what we've learned from measurements of alpha effect. It is not a linear effect.
If you are rotating in opposite directions, then it is going down?
Yes. It doesn't have the symmetry of an alpha effect. It has the symmetry of an enhanced omega effect.
Omega effect?
Take my word for it. Or do the experiment. But this one
We can do just now.
the experiment?
Yes.
You need a fluid.
First help. Being close to such a field.
Alpha effect is quadratic in the driving frequencies because the fluctuations are proportional to the rotation rate of the disk. You increase the Reynolds number, you increase the fluctuation. The fluctuations are linear in the Reynolds number. Therefore, an alpha effect which is quadratic in the fluctuation will be quadratic in the Reynolds number. And that was true in the Leonard experiment, it was true in your experiment, and it was true in the alpha effect measure in the VKS experiment with only one rotating disk.
So,
And the reason why it is quadratic is exactly what Karl Heinz was explaining. You need the velocity twice. You need it once to do this with the loop, and then you need it the second time to do this. And the amount of pumping and the amount of rotation are all produced by the same thing, the rotation of one impeller. So this is quadratic.
that is right, except that this is not alpha effect. The problem is that these wings are bent, and there is something like this disk dynamo. This current sodium between these bent plates forms something like induction, this circuit for this dynamo. And there can be this effect that this is linear.
Well, I find this argument plausible. You need the omega for producing the turbulence, the fluctuations, and then for disturbing them. Yes. Yes. That's what I learned from you now.
Yes. Okay, but at least it got me thinking about the J cross B, the J cross omega terms, and that's something that is worth it.
So when you say quadratic, is that the same quadratic thing that you have here? The term? Or
In
this one, I meant.
yes, yes. And as a result, in the measurement, when you plot the B that is induced by the alpha effect, you have a quadratic curve, not linear. So I have no.
If U dash is omega, there is another omega. Should you have omega cubed? Why square?
No, it's because when you write it like this is non-dimensional. Because you put the intensity in front of it. The rest is just what you've left out on the right hand side is just a geometry. The intensity of the motion is just on the left. And it's no more than quadratic. Bon.
But what does frequency correspond? Oh, that you mean is tau, yeah?
No, I don't know what frequency. I don't know what. I'm just saying that this is quadratic in the intensity of the driving motions, and that's all I can do. There's the relationship between what's happening really and correlation times and all. As I said again, that should be checked carefully on other points.
Of course, tau will be proportional to 1 over omega.
Well, but then, no, you can't make that argument, because if u prime is proportional to omega, then u prime tau is non-dimensional. And then of course, Agres, you can make the case that the BPS is a disk dynamo, but it doesn't do anything that disk dynamo do. So maybe our evidence is different. I had another question listening to all the talks. Is it known why in the simulations or in the experiments the hydrodynamics, the flow on which all these magnetic fields evolve are strongly turbulent, aren't they? The Reynolds number of all these flows is large.
Doesn't have to be.
Oh, it's not. Okay. So, but people assume that, say, in the sun or in the galaxy, there is a background turbulence, right?
Yes.
And is that supposed to be large?
Probably.
And if it is so, is it understood, apart from, in some physical sense, how all these processes that every time you gave a talk about the sun dynamics, and we hear about alpha and all these things, and then the sun, people involve the same thing, and the simulation involved those simple shear and alpha and all this. Is it understood why is it so robust? Why we end up with this?
With what alpha attack mean?
Yeah, it's the only mechanism, the mechanisms that are invoked seems to be stopping at two different things. Either I can deform a magnetic field line by shearing it, or I can invoke a process that will create a current parallel to that magnetic field line, whatever that process is. And no more seems to be needed. And these processes, on top of a highly turbulent background, are robust, in a sense.
But what else can you do with magnetic field?
I don't know, I'm asking. I don't know.
So what is the question whether high fluid Reynolds numbers do or do not destroy, and why they don't destroy, I mean alpha and eta t or what?
It's something that is incredibly appealing from the mean field theory,
yes.
And the pictures you get is that you seem to be able to reproduce most of the nonlinear interactions you need from those two basic principles. You can shear or you can induce a current parallel to the field line. Whatever the mechanism that is underlying it and the very many subtleties that can be to it. And is that understood why those turn out to be so robust? That when you increase Rm, you don't generate mechanisms that have higher order nonlinearity, that are more exotic, bizarre than that.
I mean, the way how it's understood so far is using mean field theory, which again breaks down for large Rms in principle. So then the question is, how come the results remain possibly correct?
What's Rm supposed to be in the sun?
Very large, 10 to the 9th, or 7th at least.
And so, and to the 10 to the 9, we still expect that those two mechanisms do the right thing. I mean, it's not a criticism in any way. It's something that I've been trying to understand over time. Yes. I'm sure we have experts here that have thought about it.
I mean, as far as the Rm dependence is concerned, we know that the idea was that possibly nothing of this survives anymore. That's exactly, I think, what you're asking, isn't it?
But so do you see where it breaks down and what more processes it generates? What, as to take Anwar's question, what else can you do? What's the new thing that comes in?
Well, this is the point. You don't know what's down the corner, right? All these non-linear effects. Now it's becoming more and more clear that they are non-trivial. It's not just, say, alpha quenching, which just it's almost quasi-kinematic solutions. That they are non-trivial. And just we discussed it after Axel talk. So there are so many unclear things. Hopefully, which is there, right? So,
but you can still model seems to be the dynamo of the sun pretty well with only these two effects. And for the galaxy, that's what you've been
well,
describing.
this is what worries me.
And that does a good job, apparently.
No, for the sun, of course, there is problems, as we discussed. Either you take the thing as you get it from the theory, and then you don't get the sun. Or you do something else, and then you do get the sun, but it doesn't come out from the theory.
But the something else as what more processes does it involve than generating a shear or a current parallel to the applied field?
How can I answer? More unknown processes. Is it a satisfactory answer?
Okay.
But you know, even with galaxies, it's not that bad. The situation is too good to be true, in some sense. The fact that these simple solutions describe the situation so nicely needs to be explained.
Yes, I think it was precisely the comment I was making. Yes. I find it remarkable.
And this can, well, I don't believe that it's just a coincidence, but this needs explanation. It shouldn't be like that. The life shouldn't be that fun.
I mean, maybe I would compare my view of the sun perhaps with the fluid motions on Jupiter, where you see really only the surface layers of Jupiter, apparently. But of course, Jupiter is deep, and it's a liquid throughout the gas. And so, how come these deeper effects, if that's really true, don't show up at the surface? Maybe they don't. But of course, at the moment, we don't know that for sure. So my picture is a more shallow one. It might actually work, but who knows? The standard picture is a completely different one, and it's a very deep picture, very deep seated dynamo, of course. We don't know. So I don't think we can talk about success here in any way. That's what you're suggesting.
But still, reproducing things again, people invoke mainly these two effects with variations, with different origins, and they seem to be doing not such a bad job at reproducing things.
But I mean,
there's inconsistencies, as you said. There's little problems here and there, but they're problems. They're not like the whole thing drops down.
No. But I mean, you need to be more specific what you are looking at. I mean, there is first of all the question about weak magnetic fields or no magnetic fields, and whether, for example, alpha and eta T survive at large Reynolds and magnetic Reynolds numbers. That's
Is there anything about magnetic vorticity? A naive idea, like if you look into the Earth and you see clouds just diffusing away and being carried by the wind, and in certain conditions the wind creates these big swirls, typhoons, right?
Mm-hmm.
So sunspots, magnetic fields on the surface of the sun, imagine that has clouds being shredded by wind, or in this case motions of the is there any kind of magnetic vorticity that can actually create the sunspot in that way?
I didn't know that Ed Spiegel has been thinking of a sunspot always being like something like a swirl, but I never understood that. We were thinking of the sunspot like a hurricane.
Yeah, it's a hurricane, yeah.
But I mean, yeah, I don't know why that should be true, but I've never seen that.
If you define velocity magnetic velocity, you take curl of D, which is current.
Yes.
It's like curl of D is omega, so it is magnetic velocity should be like curl of D, which is current. So it is a sort of a vertical picture.
You could have swirls that could be
Photograph of this.
I think I have a pretty good mental picture. I won't forget it.
It's in the camera, I hope.
I won't forget it all.
Yes. Does anybody want to respond to Jean-François' question?
Volunteers, right?
That's what I read.
Do you want to ask or bring up something else?
Are you hiring people in the next year?
Who says so?
I'm asking.
We are. We are.
So why anomaly? There's one of the web pages, of course, and maybe that's where some jobs are being announced. That's the Mac. What's it called?
Oh yes, I had 3 advertising slides which I forgot to put up. One is where the group at large is constantly hiring postdocs. So please, if you're looking for something, send us an email. Might not be at the right time, or when you send the email, the time, but there's a turnover. That's number one. Number two, you can go to the VKS collaboration websites and you can download all the data that has been published. So for any figure that we published in print, there's a matlab.fig file that has all the data in it. Okay? As people that know MATLAB know that if you download the .fig, you can recover all the points that are there. So you have the figure with the label, so you know exactly what you're looking at. It's the same legend in the papers, and you are free to play with the data points as much as you want. Okay. The only thing that is on the website and that we ask is that if you use it, please say that it's courtesy of VKS data, and all. That's all we ask. For the rest, and of course, if you find something interesting and you don't tell us, this is not nice. So that's the second advertising slide I have. The third one, if you could maybe you can pop it up, Axel. Can you pop up? There's the hydromag. Well, you don't need to pop it up. Axel was referring yesterday to Les Ouches, which I'm advertising for Les Ouches, which is, as some of you know, a good place for interactions. And as of last year, I'm the head of the of that place from the scientific point of view. So you're welcome to check what's going on there. And it's Les Ouches runs you have to add physics if you can, because there's a lot of going on in Les Ouches. Yes. Mm-hmm. Oops. Yes. So Les Ouches has a summer program where there is a school for a month, as some of you have already been, and they also have workshop year-round from January down to the end of October, and it covers all the subjects of physics. So there's 2 aspects of it, some of which you might be interested in. Do we have a program for this? I'm sure there's an English webpage somewhere.
I think it's under construction.
Yeah, it might. Under construction. All right, let me.
Put on the blackboard. A little bit more.
So like next week is a high Rayleigh number convection, and you have on the first web page on the right here, you have all the sessions that will take place. It's normally there should be an English version because all of this is in English, really. English version. There you go. Yes. So you have all the sessions that take place, and it can be biosensors, like it can be microfluidics, like it can be random metrics theory, like it can be nonlinear aspects of dynamical systems, or it covers physics. So during the workshops, and for people that would be potentially interested in organizing something here, Les Ouches hosts those week-long workshops year-round, as I said. And if you have interesting topics you want to discuss there, it's not so hard to organize something there or to participate. Skiing season is between January and March, and April is not so good. June and July is pretty good when hikes around. I'm through with the advertising.
Great, so keep that in mind. And the Hydromac letter newsletter.
And there's the Hydromac. And most of the postdocs positions, when they come out, they show up in the Hydromac letter.
Good. So with that, we could maybe close that session, and we reconvene here for Karl-Heinz's talk at 2 o'clock.
Here, right?
In the same room.